Hello, in this video I'll be showing you basically why the derivative of sine x is equal to cosine of x. So this video is basically, I'm going to be showing you using first principles why the derivative of sine x is equal to cos of x. Okay, I'll be going through I'll just show you what I'm going to be doing. Pretty much, I'll be doing a geometric representation, and I'll be using some trig identities that have been proven, and I'll be using some limits that have been proven. I'll be posting a video on the proof for one of these limits very soon. So let's just take a look at. I'll just save this document. All right. Let's take a look at the first principle. So in the last video we discussed that the gradient at any point is the limit as h approaches zero of f of x plus h minus f of x all over h. So I'm just going to draw a sine curve. So a sine curve goes like this pretty much. So f of theta equals sine theta. So this is our theta and this is f of theta. Alright, so let's just choose 2 points. Let's have this point here, which is just theta, and this is f of theta. And let's have another point here, and let's have this gap as h, and we'll have theta plus h, and this is f of theta plus h. Alright, so we record that the gradient of any line is y2 minus y1 over x2 minus x1. So our first point here is going to be theta and f of theta. And our second point is going to be theta plus h and f of theta plus h. Now, I'm just going to move this because it's in the way. We know what our function is actually. Our function f of theta is sine theta. So I'm going to change out these here for just sine. So this will be sine of theta. And this here will be sine of theta plus h. Right? So this is x1, y1, x2, y2. So for instantaneous rate of change, we want this point here to basically go on top of this point here. So this distance here needs to go to zero, not theta. Go to 0. So that's why we get our limit here. So I'm just re-establishing our first principles over here. So if we just plug these into this statement down here, we'll have y2, which is sine of theta plus h, minus y1, which is sine of theta, divided by x2, which is theta plus h, minus x1, which is theta, so that will cancel with that. And we have a limit on here, limit as h approaches 0. So this is basically our first principles here plugged in. Sine of theta plus h minus sine of theta all over h. Alright, cool. So I'm just going to rub a bunch of this stuff out now, so I have enough room to write out another, well, a formula pretty much. So I'm going to take this from this specialist mathematics curriculum, but basically you need this formula to show the proof basically for the derivative of sine x is equal to cos x. So this formula is the double angle formula. It's been proven thousands of times, millions of ways to prove it. So basically, if you have sine of the sum of two angles, so angle A plus angle B, that is equal to sine of A cos of B plus cos of A sine of B. Now there's millions of proofs for this. You can Google them online. I won't be showing you a proof for this. Well, maybe if you really want to see one, just put one in the comments. But this statement is true. It's an identity. It's not really a formula. So a formula only works for certain equations. An identity works for everything. So this is true no matter what you place into it, pretty much. Alright, so the reason, why do we need this formula for our proof on derivatives? Well, I'll show you in a bit. We're going to need to use this formula here for this term here. So I'm just going to rewrite sine, I'm going to move over a bit. Sine of theta plus h. So using our double angle formula, that's the same as sine of theta cos of h plus cos of theta sine of h, right? So using this information here, I'm just going to plug this into here, pretty much, okay? So moving this up here so you can still see it, but putting it pretty much out the row. So the limit as h approaches 0 of sine of theta cos of h plus cos of theta sine of h minus sine of theta all over h. Okay? Right. So what we're going to do now is we're going to group a couple things here. So as you can see in here, we've got sines, sine theta. So I'm just going to try and put those things together. So this this minus sine theta is acting on all of this. So it's acting pretty much. So let's say this is just a number here, and this is a number here, and this is a number here, r prime. That's pretty much, it's just basically arithmetic. So this isn't acting on individual things like this. It isn't like a distributed thing. It's basically just adding to whatever this sum in here is. And we can play around with that pretty much and just get rid of the brackets and just, we're going to group them pretty much. So I'm going to rewrite this a bit so we can take out a factor pretty much. Alright, so limit as h approaches 0. So instead of having the minus sine theta over here, I'm going to move it next to this term here. You'll see why I've done that in a sec. So I'm just going to rewrite sine of theta cos of h minus sine of theta plus cos of theta sine of h all over h. And the reason I've done that is because with this stuff here, I can take out a factor of sine of theta. So I'll just show you that in a second. Actually, first off, I'm going to split this. Oh, what did I do? Whoops. I'm going to basically cut this in half. So we can basically do this. We can cut this whole thing in half as long as the h is dividing by this whole term here and this whole term here still. It's basically like, you know when you add fractions and you have, if you have 1/4 plus 5/4, that's equal to 6/4. Well, what we're basically doing here is having 1 plus 5 over 4, and we're basically cutting this in half and making it equal to 1 over 4 plus 5 over 4. We're not changing anything, we're just changing how it looks. So we're doing the exact same thing here with these letters, okay? So I'm just going to rub this out so we have enough room, and I'm going to make a lot of this stuff a bit smaller. So I'm going to make this identity a bit smaller, move that up there, and I'm going to make this here a bit smaller too. Right? So I'm just going to rewrite this here. So I'm going to have the limit of h goes to 0 of, I'm going to factor out my sine theta of cos of h, whoops, that is very ugly looking, cos of h minus 1. So this gets multiplied out. This is all divided by h. Divided by h plus cos theta sine of h, all divided by h. So you see what I've done from this line here to that line. I've done two things. One, I've chopped my fraction in half here, just to have two different terms, and I've taken the sine theta out of these here and done it up here. So if I were to distribute the sine theta to the cos of h and -1, we would get this entire term here still. So I haven't changed anything, I haven't added anything in, I've just changed how it looks and how it appears. Alright, make this a bit smaller so we have enough room for our derivation. Okay. This is when we need to basically introduce some limits. So I won't be showing you the proof for these limits, but I will be showing proof for one of them in another video. So there's two types of there's two limits that we need to look at. So the limit of h going to 0 of the limit cos of h minus 1 over h. This limit is equal to 0. And this limit as h goes to 0 of sine of h over h, this limit is equal to 1. I will be showing a proof for this limit here in another video, but this video is strictly on the differential of sine x. So showing the proofs for both of these limits in this one video would make this video really long. So I'm only going to say these are true, and I'll provide a proof in another video. So these limits are true. Okay, so keeping those in mind, I'm just going to move them to the side so we can still have them on our screen here. Just moving that down there. Alright, so if these limits are true, we've got one of the limits, we've got this limit basically up here, and we've got this second limit up here. Can you see that? So I've got this limit here and this limit here. Those are the limits down there. So if we just substitute what they're equal to, so if we just take out our sine, if we just make these into separate limits, so we have the limit as h approaches 0 of sine theta over cos of h minus 1 all over h, plus the limit as h approaches 0 of cos theta sine h. Alright, so the theta isn't going to affect this limit, so this entire thing here is equal to 0. So I'm just going to rewrite it. I'm going to rub this all out. So that whole thing is equal to 0. So we have sine of theta multiplied by 0 plus cos of theta, and this entire limit here is equal to 1 times by 1. So we've applied these limits to both of these things here, so we don't need the limit h anymore, because we don't have a h anymore. If you multiply something by 0, it turns to 0, so we're left with cos of theta. So this whole limit of h approaches 0 is our first principles, otherwise known as the first derivative, f dash of theta. So f dash of theta is equal to cos theta. Therefore, the derivative operator with respect to x, actually no, let's do theta to keep our variable straight. The first derivative of sine theta is equal to cos theta. Or what you might see it is dx of sine of x is equal to, not sine of x, cos of x. Cos of x. The only difference between these two things here is I've just changed my variable from a theta to an x. Alright, so that was the proof using first principles that the derivative of sine of x is equal to cos of x. I'll be making a proof now on this limit down here now, so I'll be posting that pretty soon. I hope you learned something in this video. If you want to learn anything, anything in particular, just leave something in the comments. I'll do a video on it. Alright, thank you.